There are places in the universe where the laws of physics unravel, where time stretches into eternity and gravity becomes an artist sculpting matter into terrifying shapes, places where the known collapses into the unknowable and where science stares into the abyss and gets no answer, only silence. These Anomalies so foreign, so violently indifferent science fiction, but real phenomena, observed, measured, and still not fully understood, and they may hold the key to understanding what the universe is, where it came from, and where it's heading. Take black holes, for example. Born from the death of massive stars, they are not merely celestial objects but fractures in space-time, places where mass is compressed into infinite density, creating singularities where the known laws of physics no longer apply, where time slows to a crawl at the event horizon and stops entirely at the core, and where not even light can escape the grip of gravity, making them invisible unless they feed tearing apart stars and devouring matter in spiraling, luminous dances that light up entire galaxies with X-rays and gamma rays that scream across the cosmos. Yet some black holes defy expectations entirely, like the ultramassive ones discovered at the centers of galaxies far too young to have had time to grow them through normal accretion, challenging our understanding of cosmic evolution and suggesting that perhaps there were black holes before there were galaxies at all, and perhaps even before the stars themselves were born. Then there are rogue planets, giant worlds cast out of their solar systems, drifting alone through interstellar space without a sun, frozen and dark but not dead, because some of them retain internal heat, perhaps even harboring oceans beneath layers of ice, raising haunting questions about whether life could exist even in the most abandoned corners of the universe. Born not from sunlight but from geothermal whispers beneath a crust of eternal night. And what about fast radio bursts, enormous pulses of energy lasting milliseconds, brighter than a billion suns, coming from distant galaxies, yet leaving behind no clear signature of their origin, blinking into existence and vanishing just as quickly, some repeating like cosmic Morse code, others never again are they, from magnetars spinning themselves into insanity, from neutron stars colliding, or from something far stranger that we don't yet have words for, let alone equations. And what of the great Attractora gravitational anomaly in space, pulling entire clusters of galaxies, including our own Milky Way, toward a region we can't even see, obscured by the dust and stars of our own galactic plane? Yet we feel it, we measure it, and we are helplessly moving toward it at over 2 million kilometers per hour, like moths drawn toward something massive, unseen, and maybe unknowable. Or the cold spot in the cosmic microwave background region of the early universe's afterglow that is significantly colder than expected, an apparent violation of the otherwise smooth temperature fluctuations across the sky, which some think might be a statistical fluke, others suspect a supervoid, and some propose it's the fingerprint of another universe colliding with ours in the distant past, a bruising scar left over from a time before time, hinting that the multiverse isn't just theoretical poetry but something that has left evidence on the cosmic canvas. And quantum entanglement, which Einstein dismissed as spooky action at a distance, now proven real and foundational to our understanding of reality, defies locality and suggests particles, once linked, remain connected no matter the distance, as though space itself is an illusion, as though the very fabric of what we call reality is woven not from matter but from relationships, from probabilities, from patterns in the void. And this leads us to the simulation hypothesis, a philosophical and scientific rabbit hole, where some physicists argue that the precision and structure of physical law, the uncanny simplicity of mathematical constants, and even the quantized nature of reality at its smallest scales all suggest that the universe might not be analog but digital, that we could be living inside a computational framework so vast and refined that we only perceive it as natural because we were born inside it? A thought that once belonged to science fiction but is now debated in peer-reviewed journals and lectures by respected physicists. And if that isn't strange enough, consider the discovery of dark matter and dark energy together, making up 95% of the universe, yet completely invisible, undetectable by direct means, their presence only inferred by the way they warp space, bend light, accelerate the expansion of the universe, and defy every prediction made by classical models, and yet we still have no idea what they are. No particle found, no theory complete, only shadows cast by invisible giants that dominate the cosmos without ever revealing themselves to us, as if the universe is mostly made of secrets. And yet among all these anomalies, perhaps the strangest is used beings made of atoms forged in the hearts of stars, capable of asking questions about time and space and reality, capable of building machines that see to the edge of the visible universe and to the beginning of time itself, of decoding light from billions of years ago and translating it into meaning, of contemplating the infinite and the eternal and still arguing about what to have for lunch as if we are a contradiction in motion. Proof that consciousness is itself an anomaly the universe has created to observe its own strangeness. Because the more we discover, the more bizarre the universe becomes. And each new answer opens 10 new questions. Each solved puzzle reveals another, and the deeper we go, the more it seems that reality is not what it seems, that beneath the familiar lies the uncanny, and beneath the uncanny lies something utterly alien. And it is precisely this, the layered strangeness, the vertigo of comprehension, the sublime awe of confronting what cannot be tamed into simple understanding that makes science not just a method but a mythic quest, a search for the soul of the cosmos, in a place where there may be no center, only infinite outwardness, a horizon that recedes the closer we approach, a tapestry of anomalies woven together into something terrifying, beautiful, and endlessly mysterious. In the earliest chapters of human history, long before telescopes or satellites, people looked up at the night sky and built stories out of the stars, mapping constellations that guided their migrations, their harvests, and their myths. And in those stories, the universe was small, ordered, and often divine. A dome above a flat Earth, or a series of crystalline spheres holding the planets and stars in perfect celestial harmony. And for thousands of years, this geocentric view especially, the model formalized by Ptolemy, defined the human understanding of the cosmos, accepted not only for its apparent accuracy in predicting the movements of the heavens, but also for the way it aligned with religious and philosophical beliefs about humanity's central place in creation. But all of that would begin to unravel in the 16th century, when a Polish mathematician and astronomer named Nicolaus Copernicus proposed a radical idea that the Earth was not the center of the universe, but merely one of several planets orbiting the Sun. And though his heliocentric model was mathematically elegant and more accurate in predicting planetary motions, it faced fierce resistance for dethroning humanity from its cosmic pedestal. Yet, over the next century, observational evidence began to build, thanks to men like Galileo Galilei, who, using one of the first telescopes aimed at the heavens, observed moons orbiting Jupiter, proving that not everything revolved around the Earth, and who saw the phases of Venus, confirming the Copernican model and dealing a fatal blow to the old world view. And though his work brought him into conflict with the Catholic Church, it laid the foundation for a new way of thinking, one rooted in empirical observation and the willingness to challenge long-held beliefs in the face of evidence. Johannes Kepler followed with his laws of planetary motion, describing elliptical orbits and rejecting the notion of perfect circles in the heavens. And then Isaac Newton revolutionized our understanding of the universe by formulating the laws of motion and universal gravitation, showing that the same force that caused an apple to fall from a tree also governed the movement of planets and stars, uniting the heavens and earth under a single mathematical framework, and marking the beginning of classical mechanics, a model of the universe that would dominate science for over 2 centuries, a universe that was vast, ordered, and comprehensible, if not yet infinite. As telescopes grew more powerful, astronomers began to catalog thousands of stars and nebulae, and the 18th and 19th centuries saw the birth of astrophysics as scientists began to analyze light from distant objects, discovering that stars were not just points of light but suns in their own right, composed of the same elements found on Earth. And this revelation helped further dethrone humanity's sense of cosmic uniqueness. Then came the 20th century, a period of seismic shifts in cosmology, beginning with Albert Einstein's theory of general relativity in 1915, which replaced Newton's concept of gravity as a force with the idea that mass and energy warp the fabric of spacetime. And while Einstein himself initially believed the universe was static, he introduced a mathematical fudge factor called the cosmological constant to keep it from collapsing under gravity. But soon after, in the 1920s, a Belgian priest and physicist named Georges Lemaitre proposed that the universe was expanding, having originated from a primeval atom, a concept that would later become the Big Bang Theory. Around the same time, Edwin Hubble, observing distant galaxies through the 100-inch Hooker telescope, discovered that these galaxies were not only outside our own Milky Way contrary to prior assumptions, but that they were moving away from us, and the farther away they were, the faster they receded, a relationship now known as Hubble's law. And this discovery, perhaps more than any other, forced scientists to abandon the idea of a static universe and accept that the cosmos was dynamic, expanding, and evolving over time. The implications were staggering. If the universe was expanding, it must have once been smaller, denser, and hotter, leading to the idea of a cosmic beginning. And over the next few decades, this theory gained support from multiple lines of evidence, most notably the discovery of the cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilsona faint uniform glow permeating all of space, the afterglow of the Big Bang itself, a fossil of the universe's birth imprinted on the fabric of reality. As the Big Bang model gained prominence, scientists also began to uncover other layers of cosmic history, such as the process of nucleosynthesis, the formation of elements like hydrogen and helium in the first few minutes after the Big Bang, and the way tiny fluctuations in the early universe gave rise to the vast cosmic web of galaxies and voids we observe today. The field of cosmology matured rapidly, branching into new theories and models, including inflation theory, proposed by Alan Guth in the 1980s, which posited that the universe underwent a period of exponential expansion in the first fraction of a second, smoothing out irregularities and explaining the large-scale structure we see today. Meanwhile, space exploration was transforming humanity's relationship with the cosmos in parallel, beginning with the launch of Sputnik by the Soviet Union in 1957, the first artificial satellite, and followed by the monumental achievement of Apollo 11 in 1969, when Neil Armstrong and Buzz Aldrin became the first humans to walk on the moon, marking not just a technological triumph, but a symbolic moment in our quest to reach beyond the Earth. Over the next few decades, robotic missions explored the planets of our solar system, sending back breathtaking images of Martian deserts, Jupiter's storm-racked clouds, Saturn's icy rings, and the mysterious terrains of moons like Europa and Titan, while the Voyager probes carried humanity's message into interstellar space, bearing golden records filled with music, greetings, and the sound of a heartbeat, as if hoping to whisper our story to the stars. At the same time, space-based telescopes like Hubble, launched in 1990, gave us an unprecedented view of the universe, capturing images of distant galaxies, stellar nurseries, and dying stars with clarity and depth previously unimaginable, helping to refine our models of cosmic evolution and discover thousands of exoplanets orbiting distant stars, rekindling ancient questions about whether we are alone in the universe. The 21st century has brought even more astonishing developments, including the detection of gravitational waves in 2015 by LIGO, confirming a key prediction of Einstein's general relativity and opening a new window on the cosmos, allowing us to listen to the ripples in space-time created by cataclysmic events like black hole mergers and neutron star collisions. And more recently, the launch of the James Webb Space Telescope in 2021 has allowed us to peer deeper into the universe's infancy, observing galaxies as they appeared just hundreds of millions of years after the Big Bang, and finding that even the earliest structures were surprisingly massive and well-formed, challenging existing theories of galaxy formation and suggesting that our cosmic timeline may need revision. Parallel to these observational breakthroughs, theoretical physics has pushed the boundaries of our understanding with concepts like dark matter, an invisible substance that exerts gravitational influence but emits no light and dark energy, a mysterious force driving the acceleration of the universe's expansion, both of which are now thought to compose the vast majority of the universe's mass-energy content, yet remain elusive and poorly understood, prompting new experiments, new detectors, and new theories that range from supersymmetry and string theory to extra dimensions and quantum gravity. Amid all of this complexity and mystery, scientists have come to define the concept of the observable universe, a sphere roughly 93 billion light-years in diameter, centered on Earth not because of any special status, but because it represents the portion of the universe from which light has had time to reach us since the Big Bang. Limited by the finite speed of light and the age of the cosmos, and beyond this horizon may lie vast regions forever inaccessible, perhaps infinitely many galaxies, or perhaps something else entirely, regions governed by different physical laws or initial conditions, if inflation and multiverse theories are correct. And so, the story of how humanity came to understand the universe is not a tale of steady progress, but of revolutions, each one more humbling, each one stripping away illusions of centrality and simplicity, and each one revealing a cosmos that is older, stranger, and more magnificent than the last. And yet, through it all, the unifying thread is curiosity, the insatiable desire to know, to look outward and understand not just the stars, but the rules by which they shine, and in doing so, to understand something essential about ourselves, that we are part of this universe, woven from its atoms, born of its energy, and capable of reflecting on its vastness in a way no other known form of matter can. Imagine standing under a night sky so dark and so clear that the stars seem close enough to touch, each one a burning sun thousands of light years away. Each one part of a story that began billions of years ago and will continue long after we're gone. And in that moment, something primal awakens in you, a quiet sense of awe, maybe even vertigo, as if the vastness above is pulling at something deep within your soul, and you can't quite explain why, but you feel it. That strange mix of wonder and insignificance, of beauty and terror, of being both a part of the universe and entirely lost inside it. And it's in that feeling that the emotional power of cosmology lives, not in equations or telescopes or datasets, but in the raw, unfiltered experience of trying to comprehend a universe that is at once breathtaking and terrifying. And the truth is, people should care about the universe because the universe is not something separate from you, it is us. It is everything we are and everything we will ever be. Every atom in your body was forged in the core of a dying star. Every breath you take contains molecules older than Earth. And every thought that sparks in your brain is the product of a billion-year chain reaction that began with hydrogen, gravity, and time. And when you look up at the sky, you are not just seeing stars. You are looking into a mirror that reflects your deepest questions. Where did I come from? Why am I here? What happens after this? These are not abstract questions. They are the foundations of human consciousness, of art and religion and science. And even if you never learn the names of constellations or the temperature of neutron stars, you are still tethered to the cosmos by your own existence, by the mystery of how a creature capable of asking questions about the edge of the universe can be made from the same material as dust and stone and fire. The emotional resonance of the universe lies in its extremes, its infinite scale, its ancient past, its unimaginable forces, and perhaps most powerfully, in its silence, because the universe does not care about us. It does not answer. It does not comfort. It simply is. And in that silence, we are left to find meaning ourselves. And maybe that's why it affects us so deeply. Because in a world full of noise, the universe gives us silence. In a world full of distractions, it offers stillness. And in a world full of certainty and deadlines and routines, it gives us the unknown, the unanswerable, the eternal. And whether that fills you with hope or dread or something in between, it stirs something human, something ancient, something sacred. The fear of the cosmic void is real, and it's valid when you realize how small Earth is, how fragile life is, how thin our atmosphere is compared to the crushing pressure of gas giants or the emptiness of intergalactic space. It can be overwhelming. It can feel like nothing matters, like we're accidents on a pale blue dot orbiting a mediocre star in a forgettable corner of a galaxy among trillions. But that perspective can also be liberating. Because if we are so small and yet capable of love, of thought, of beauty, then our significance isn't about size or permanence. It's about consciousness. It's about presence. And in the face of a universe that neither punishes nor protects us, we are free to define our own meaning, to make art, to reach out to others, to explore not because we must, but because we choose to, and that choice is everything. There's something uniquely human about our relationship with the cosmos, are the only known species that tells stories about the stars, that names them, that maps them, that builds machines to chase their secrets across the vacuum. And this isn't just a scientific endeavor, it's a deeply emotional one, driven by longing, by curiosity, by that relentless desire to know, to pull back the curtain and glimpse whatever lies beyond. And whether that curiosity leads us to Mars, or to exoplanets orbiting alien suns, or to gravitational waves echoing from a time before time, the journey itself is a testament to something noble in us, something that refuses to be content with ignorance or simplicity. When children look up at the sky and ask, "What is that?" or "Are we alone?" they are not asking for trivia. They are asking to belong, to be part of a story that's bigger than school or bills or borders. And they are right to ask, because the story of the universe is not separate from Use-Its, the only story there is. And every scientific breakthrough, every philosophical reflection, every poetic metaphor that tries to capture the stars is an attempt to remember where we came from and where we might be going. In the coldest corners of deep space, there are orphaned planets with no sun, rogue black holes drifting through the void, galaxies colliding in slow, billion-year dances, and yet, here we are, huddled around a small fire on a tiny rock, talking about it, dreaming about it, turning the chaos into knowledge and the emptiness into inspiration. And that should make you care, because to be human is to reach for things beyond your grasp, to imagine the unseen, to mourn the loss of certainty and still find the courage to ask questions that have no answers. And in doing so, we become more than biology. We become part of a legacy that stretches from the first spark of life to the first telescope to the first step on another world. The cosmos can make us feel small, but it can also make us feel vast. Because when you contemplate the lifespan of stars, the death of galaxies, the fabric of space-time, you are participating in an active scale so immense and so rare that it borders on the spiritual. And whether or not you believe in a creator or a multiverse or nothing at all, the emotional impact of staring into the infinite and realizing you are alive now, in this brief window of awareness, is something sacred in its own right. The fear, the awe, the humility, the hope, all of it is real, all of it is valid, and all of it matters. Because in a universe that doesn't owe us anything, we have found beauty anyway. We have built meaning anyway. We have loved and lost and dreamed and discovered anyway. And that makes the cold darkness of space feel just a little warmer, a little more like home. When you learn about the universe, you are not just learning facts, you are learning how to see, how to feel, how to wonder again. Like a child seeing fireflies for the first time, or hearing music that makes them cry. And that emotional connection, that deeply human thread of curiosity and courage and humility, is the heart of why this matters. Not because we need to know everything, but because in trying, we become something extraordinary, something the universe never expected, and maybe never intended beings who can imagine the end of time and still find the strength to get out of bed and live another day. And maybe that's the real gift of the cosmos. Not answers, but perspective. Not certainty, but the reminder that life, for all its pain and confusion, is rare, is fleeting, is precious, and is made even more beautiful by the vast mystery in which it unfolds. What if the universe is not what we think it is? What if the boundaries of our reality are not defined by what we can see, touch, or even measure, but by the questions we dare to ask? What if the most important truths about existence are still hidden in the blackness between the stars, waiting to be revealed not by some distant alien civilization or divine revelation, but by USB curious minds that refuse to settle for what's already known? When you look up at the night sky, do you see emptiness or do you see potential? Not just the potential for new planets or habitable worlds or alien life, but the potential for us to change how we understand everything: space, time, reality, and even ourselves. Could it be that our understanding of physics is just a fragment of a larger framework, one that includes dimensions we can't perceive, particles we've never imagined? Or forces that lie completely outside our current theories? These aren't just rhetorical questions, they're active frontiers of modern science, being explored by astronomers, physicists, and philosophers alike. And the more we learn, the more the universe seems to ask of us in return. To reimagine what we believe is possible. Imagine waking up one morning to a discovery that shatters everything we thought we knew, a message from another civilization, a wormhole detected near Jupiter, or a quantum experiment that proves reality is fundamentally conscious. How would that change your day? Your relationships? Your sense of purpose? Would your daily worries still feel the same if you knew you were living in a universe filled with intelligent life, or infinite timelines, or hidden realms of spacetime? These aren't just wild ideas, they're questions grounded in serious scientific pursuit, and whether they are answered in our lifetime or far beyond it, the act of engaging with them brings us closer to something we all crave: meaning. Because mystery, especially on a cosmic scale, isn't a void, it's an invitation. It's a spark that lights the fire of imagination, a doorway into a deeper sense of being alive. And when we invite these questions into our lives, we begin to see the ordinary differently. A drop of water becomes the result of planetary chemistry. A flicker of starlight becomes a story billions of years old. A glance at the moon reminds us that humans walked there, and may soon walk much farther. So, ask yourself this: what are the limits of your understanding? Have you ever truly confronted the scale of time, the depth of space, or the possibility that you are made of particles that obey rules even the greatest minds don't yet understand? When you consider that every second, the universe is expanding faster than the speed of light at its edges, and that entire galaxies are vanishing beyond the cosmic horizon, becoming permanently unreachable, does that make you feel helpless or inspired? Does it make you want to look away or look closer? Because here's the strange paradox: the more insignificant we seem in the cosmic scale, the more miraculous our awareness becomes. In a universe where most matter is dark, most energy is unseen, and most of space is empty, the existence of beings who wonder, dream, build, and ask, why, is statistically absurd, and yet, here we are. That makes the search for answers not just a scientific mission, but a human one. Every time a new telescope is launched or a probe is sent beyond our solar system, we are not just gathering data, we are engaging in a conversation with the cosmos, one question at a time, and your voice is part of that dialogue. You don't have to be a scientist to ask the big questions. You don't need a degree in astrophysics to wonder what came before the Big Bang, or whether time has a beginning and an end, or what consciousness really is. You just need to care, to be curious, to keep looking up and asking, what if? And if you're willing to do that, you become part of the greatest adventure our species has ever undertaken, the journey to understand the unknown. Think about the impact of future discoveries. What if we find microbial life on Europa or Enceladus, confirming that life can arise in more than one place in the universe? What if we detect technosignaturous signals from alien civilizations that prove we're not alone? What if quantum gravity unlocks the secret to unifying general relativity and quantum mechanics, revealing that space-time is emergent and the universe is a simulation after all? These aren't science fiction dreams anymore. They're real lines of inquiry being pursued in labs, observatories, and equations right now. The consequences would be enormous, not just scientifically, but philosophically, ethically, emotionally. How would society respond? How would religion, politics, art, and human identity evolve in the face of those truths? Would we unite as a species, recognizing our shared place in the cosmos? Or would we fracture even more under the weight of the unknown? These are the questions worth asking, not because we have answers, but because the act of asking changes us. It stretches our perspective, humbles our ego, expands our imagination. And most importantly, it connects us, because no one can explore the universe alone. It takes collaboration, discussion, disagreement, and wonder shared across boundaries of language, culture, and belief. So, talk about it. Share your ideas. Debate your theories. Ask your friends what they think is at the edge of the universe, or what they believe existed before time began. or whether they think we'll ever upload consciousness into a quantum substrate and explore the stars as digital travelers. These conversations matter not because they're practical, but because they are deeply human, and they remind us that behind every telescope and particle collider and line of code is a person who asked a question they didn't know how to answer and tried anyway. And now it's your turn. Ask yourself, what if the universe is not a thing, but a question? What if our lives aren't just about survival or success, but about understanding our place in something unimaginably vast and ancient and full of stories we've barely begun to hear? What role will you play in that story? Will you be a silent observer, content with what is handed to you? Or will you be a seeker, a builder of questions, a dreamer of possible futures? Because the unknown isn't going away. It will always be there, lurking in the blackness beyond our instruments, humming behind the equations we don't yet understand, whispering through the gaps in our most advanced theory. And the more we look, the more we find, and the more we find, the more we realize we've only just begun. That's the challenge and the gift of the universe, to awaken us, to stretch us, to show us that while we may be small, we are not irrelevant, because relevance comes not from size, but from awareness, and we are aware. So if this stirs something in you, if some part of you wants to keep exploring, to keep asking, to keep engaging, then don't let that go. Feed it, talk about it, write about it. Create art that expresses it. Build communities around it. Follow the science. Challenge the dogma. Encourage others to wonder, especially those who've been told not to. Because the universe belongs to all of us, not just the experts, not just the dreamers, not just the machines pointed skyward. It belongs to anyone who dares to ask what's out there and what it means that we're here. The most powerful force in the universe may not be gravity or electromagnetism, it may be curiosity, and it lives in you. Let it grow. Let it lead. Let it be the spark that lights someone else's journey into the unknown. And in doing so, you become part of something truly cosmic, not just a witness to history, but a participant in the evolution of understanding itself. The universe is not finished revealing itself, and you are not finished becoming who you were meant to be in light of what's still to come. Space is not empty. It is not silent. It is not still. It is a living tapestry of force and fire, of birth and annihilation, of structure beyond comprehension and chaos beyond control. It stretches across time, not just distance, wrapping the present in the aftershocks of ancient detonations and whispers from galaxies too distant to ever be reached. Yet still they speak, their light crossing billions of years to arrive, delicate and undisturbed, into the lens of a telescope aimed upward by a human hand. The universe is a cathedral of extremes, where the walls are made of time, the pillars of gravity, and the ceiling has no end. When you close your eyes and picture space, what do you see? Darkness? Emptiness? You're wrong. Look closer. Between the stars lies the interstellar medium, a thin haze of dust and gas, ionized and heated by nearby supernovae, glowing in the faintest shades of crimson and ultraviolet. Within that soup, new stars are born in turbulent clouds called nebulae, where shock waves from dying stars compress hydrogen into glowing pockets of light, and fusion begins anew, each one a furnace of creation. These stellar nurseries can span dozens or even hundreds of light years, places like the Eagle Nebula's pillars of creation, vast towers of gas being eroded by the radiation of newborn stars. Each beam of light a signal of emergence, of transformation, of the constant cycle that defines the cosmos. These stars gather in galaxies' collections of hundreds of billions of suns bound by gravity, swirling like cosmic whirlpools, each galaxy moving through space, colliding with others, warping each other's shapes in dances that last billions of years. The Milky Way, our own home, is one such spiral galaxy, a vast disk of stars and dark matter turning like a wheel through intergalactic space. And somewhere in one of its spiral arms orbits a yellow star with a handful of rocky worlds, one of which has oceans and forests and cities and minds that dare to wonder what lies beyond. Yet galaxies are only the beginning. Between them are gulfs so large they defy analogy, distances so vast that light itself, moving at 300 kilometers per second, takes millions of years to cross from one side to the other. But even this isn't the largest structure. Galaxies cluster into groups, and groups into superclusters, connected by filaments of dark matter and gas that form a cosmic web, an enormous structure that resembles neural networks, or the branching of lightning, or the blood vessels in a living creature. And in between these strands lie the great cosmic void cements, near empty regions where few galaxies dwell, and where the silence of the universe is almost total. These voids are not nothing, they are space itself, expanding and stretching, carrying the galaxies farther and farther apart. It is in these places, these yawning gaps of near absolute nothingness, that the full weight of the cosmos can be felt, the sheer scale, the terrifying quiet, the beauty of a universe so large it becomes impossible to visualize. And behind all of this, behind the stars, behind the galaxies, behind the light lurks something even stranger: dark matter and dark energy, the twin enigmas of modern cosmology. Dark matter is not some myth or placeholder, is real, and we know it's there because we can see what it does. It binds galaxies together, preventing them from flying apart. It bends the light from distant galaxies, causing gravitational lensing, where massive objects distort the light behind them, like glass warping an image. It does not emit light, does not reflect it, and so far we've never detected it directly. But its fingerprint is everywhere. Without dark matter, the universe as we see it would not exist. Then there is dark energy, even more baffling, an invisible force causing the expansion of the universe to accelerate, as if space itself were stretching faster and faster, dragging the galaxies apart with increasing speed. Discovered at the end of the 20th century through careful measurements of supernovae, dark energy now accounts for nearly 70% of the total energy of the universe, and yet we do not know what it is, why it exists, or if it will one day tear the universe apart in a final, irreversible unraveling of space-time called the Big Rip. These aren't fringe ideas, they are central to the best current models of the cosmos, and they have transformed how we understand reality. At the center of this grand investigation are the people, those who look up and ask, again and again, what is this place? Figures like Edwin Hubble, who first proved that the universe extends far beyond our galaxy, and that it is expanding. Albert Einstein, whose theory of general relativity replaced Newton's clockwork universe with a dynamic fabric of space-time, one that bends and warps in response to mass and energy. Vera Rubin, whose meticulous measurements of galactic rotation curves provided the strongest early evidence for dark matter long before the term became popular. Stephen Hawking, who explored the behavior of black holes and the edges of time, proposing that singularities were not just mathematical artifacts, but real places in space-time, and that black holes might even evaporate slowly through Hawking radiation. And modern visionaries like Kip Thorne and Andrea Ghez, whose work helped confirm the existence of black holes through direct imaging and gravitational wave detection, an achievement that merged theory with observation and opened an entirely new way to study the universe. There's also the unsung army of cosmologists, physicists, engineers, and data scientists who work behind the scenes, who design the instruments, interpret the signals, map the sky, and build simulations that recreate the birth of galaxies, the collision of neutron stars, the murmur of the Big Bang itself. From labs deep underground hunting for dark matter particles to radio telescopes scanning for whispers from ancient quasars, this is a human story, as much about dedication and curiosity as it is about stars and voids. It is a story of late nights and failed experiments, of numbers that don't line up and mysteries that deepen instead of resolve, and yet still, we keep going. The tone of all of this, of galaxies spinning and stars dying and voids expanding, is one of awe, not cheap wonder, but the kind that leaves you breathless, the kind that forces humility, the kind that makes you realize how vast the unknown truly is. There's mystery, yes, but not mystery that paralyzes. This is the kind that invites you to explore. A type of curiosity so deep it becomes its own kind of faith, not in dogma or certainty, but in the belief that the universe is knowable, piece by piece, question by question. And for every answer we do find, like the detection of gravitational waves from colliding black holes, there are a dozen new questions waiting in the wings. What lies inside a black hole's event horizon? Why did inflation happen? What caused the matter-antimatter asymmetry that allowed the universe to exist at all? Are we living in one of many universes, each with its own physics? And perhaps the most haunting of all, why is there something rather than nothing? To immerse yourself in the cosmic setting is to accept a paradox that the universe is both intimate and unreachable. That the particles in your body once danced inside stars, and yet the stars themselves are forever beyond your touch. That we are made of the cosmos, and yet separated from it by unimaginable distances and timescales. But this is not cause for despair, it is cause for reverence. It means that knowledge is possible, that wonder is not a weakness, but a strength, that science is not cold, it is the language of awe made rigorous. So stand with your feet on the earth and look up. Imagine the photons hitting your eyes were released before the first human walked upright. Imagine the voids between galaxies, so vast they could contain millions of Milky Ways and still be nearly empty. Imagine the symmetry of the early universe, the ripples in the cosmic microwave background, the hidden forces threading galaxies together, the ancient stars whose deaths seeded planets with iron, oxygen, and carbon, the very elements of your bones and blood. Imagine the people who've spent their lives deciphering these stories, and the ones who will carry that torch long after you and I are gone. We are not separate from this cosmic story. We are chapters in it. We are, quite literally, the universe becoming conscious of itself. And that is the atmosphere we live in, not one of isolation, but one of connection, not one of finality, but of perpetual discovery, not a silent, empty void, but a dynamic, pulsing, radiant cosmos whose deepest phenomena are just beginning to speak, and whose greatest revelations still lie ahead. It begins with a question as old as thought itself. Where does it end? Not just the stars, or the galaxies, or the observable reach of our instruments, but the universe itself. Is there a wall, a boundary, an edge to reality? Can we sail far enough across the cosmic sea to find the place where space stops, where time runs out, where nothing exists beyond? These aren't idle questions, nor are they easily dismissed as philosophical abstractions. They are at the very heart of cosmology, of our attempt to not just map the stars, but to grasp the shape and structure of everything that is. And yet, the deeper we dig, the more it seems the edge may never be found, not because it doesn't exist, but because it might lie beyond the reach of observation, comprehension, and even imagination. From the earliest moments of cosmic discovery, paradox has followed us like a shadow, revealing not just how much we know, but how fragile that knowledge truly is. We used to think the universe was static and eternal, until Einstein's equations suggested otherwise, and Hubble's observations confirmed the expansion. We believed the Milky Way was the whole of existence, until galaxies proved otherwise. We assumed the universe obeyed a neat, Newtonian order, until relativity bent time and warped space. And just when quantum mechanics emerged to explain the microscopic world, we discovered it directly contradicted the smooth determinism of general relativity. Two of our best, most tested theories, Einstein's gravity and quantum field theory, function beautifully on their own, but are fundamentally incompatible at the scales where both should apply, like the interior of a black hole or the first instant after the Big Bang. This is not just a technical inconvenience, it is a signpost, a crack in the foundation, suggesting that our understanding of reality is incomplete in ways we do not yet have the language or tools to resolve. Even our most basic assumptions are now under scrutiny. Space and time, once thought to be the backdrop against which the universe plays out, may be emergent phenomena, born from something deeper, perhaps quantum entanglement, perhaps something even stranger. The very idea of an edge becomes complicated when space itself can bend, twist, loop, or expand faster than the speed of light. Not in violation of physics, but because space is not a thing moving through something else, it is the something else. If the universe is infinite, then there is no edge-only, endless repetition, or unimaginable variation. But if it's finite, then what lies outside? If it's curved, is it like the surface of a sphere, edgeless yet bounded? And if there is a boundary, how would we even know? Light takes time to travel, and we are limited by the age of the universe, about 13.8 billion years, and the speed of light. The observable universe may be about 93 billion light-years in diameter, but that is only what we can see, not what exists. Beyond that lies a realm we cannot reach, not because of technology, but because of the very laws of causality and expansion, which stretch space faster than light can cross it. The concept of cosmic inflation makes things even stranger. According to this theory, the universe expanded exponentially in the first trillionth of a second after the Big Bang, growing from subatomic size to something macroscopic in a flash. This smoothed out the universe and explains why distant parts look similar, but it also means the universe may be much larger than we can observe, possibly infinite, and that inflation never stopped, but continues in other regions, creating pocket universes with different laws of physics. This is the multiverse hypothesis, and while it sounds like science fiction, it is a natural implication of many inflationary models, supported by string theory and quantum cosmology. But here's the problem. These other universes, if they exist, are forever beyond our reach. We can't see them, touch them, test them. They lie beyond the cosmic horizon, and always will. This raises a deep and troubling issue in science. If something cannot be observed, even in principle, can it still be part of scientific theory? And if the answers we seek lie in these unreachable regions, will we ever be able to claim we know the truth? Even within the observable universe, we face hard limits. We look to the sky for light from the earliest galaxies, and thanks to telescopes like Hubble and now James Webb, we can peer back more than 13 billion years. But we can't see the actual moment of the Big Bang, not because it was hidden, but because before 380 years after the event, the universe was opaque, a hot plasma of particles and photons colliding too frequently for light to travel freely. Only when it cooled enough did light decouple from matter, creating the cosmic microwave background radiation, the earliest observable surface of the universe, like a fog lifting. Beyond that lies a wall, not of matter, but of information. We cannot see past it using light. Neutrinos or gravitational waves might offer a deeper glimpse, but even they are bound by practical and theoretical barriers. Our instruments, no matter how advanced, are blind beyond certain horizons. We are cosmic archaeologists, digging through layers we can never fully penetrate. And then there are the paradoxes, subtle, maddening, and deeply unsettling. The black hole information paradox, for instance, asks whether information that falls into a black hole is lost forever. According to quantum theory, information cannot be destroyed. According to general relativity, it disappears inside the event horizon. Both can't be true, and yet both are foundational. This conflict has pushed physicists toward ideas like holography, notion that the universe might be a projection of information encoded on a distant boundary. If true, then everything we experience, from galaxies to consciousness, may be a kind of emergent illusion, the shadow of a deeper reality we can't directly observe. Similarly, quantum entanglement challenges our notions of locality, suggesting that particles separated by light years can instantly affect each other, defying our classical understanding of space and time. Are we wrong about distance itself? Is reality non-local at its core? We also face the challenge of technological and human limitations. Instruments can only measure so finely. Detectors have noise, errors, blind spots. Our brains evolved to survive in jungles and savannas, not to visualize 10-dimensional space or parse quantum fields. Mathematics extends our reach, but interpretation remains a human endeavor, filtered through cognition, culture, and metaphor. And as our theories grow more abstract, they risk becoming untethered from testable predictions. String theory, for all its elegance, has yet to produce falsifiable outcomes. Theories of loop quantum gravity remain speculative. Efforts to unify physics, the theory of everything, have yielded brilliant math, but few answers. We may be approaching what some call the epistemic horizon, a point beyond which further understanding is blocked not by unwillingness, but by the fundamental nature of the universe and our place within it. And yet, we continue, because the conflict itself is part of the story. The tension between what we know and what we can never know is not a failure. It is the engine of progress, the spark of inquiry, the mirror we hold up to the cosmos and to ourselves. Perhaps the true edge is not a boundary in space, but a boundary in thought, a place where our models break down, where our assumptions no longer hold, where certainty dissolves into possibility. That edge is not static. It shifts as we learn, recedes as we advance, taunts us with each new breakthrough that only deepens the mystery. We do not know whether the universe is infinite or finite, closed or open, eternal or doomed. We don't know what happened before the Big Bang, or if before even makes sense. We don't know what dark energy is, why the constants of nature have the values they do, or whether consciousness is a byproduct of matter or a fundamental feature of reality. These aren't flaws in our science. They are signs that we are asking questions that matter, questions that push against the very structure of knowledge, questions that force humility and invite imagination. And they suggest that the search for the true edge, the final answer, the ultimate map, the full equaciones, perhaps not the goal at all. Perhaps the edge is meant to remain out of reach, not as punishment, but as promise. A reminder that the universe is not something to be solved, but something to be lived in, wrestled with, danced around, forever mysterious and forever meaningful. So when we speak of conflict in cosmology, we are not talking about wars or rivalries. We are talking about the clash between what we can observe and what we suspect lies beyond. The friction between the finite mind and the infinite expanse. The dissonance of having equations that work yet cannot be unified. The aching beauty of a question without an answer. And in that conflict lies the essence of our journey, not to find the edge and stop, but to move forever toward it, knowing it will always move too, just beyond the limits of our reach. Just far enough to keep us wondering, asking, reaching, becoming. There is a war raging at the heart of modern cosmology, though its battlefield is not marked by fire or blood, but by chalkboards filled with equations, supercomputer simulations of infant galaxies, and silent observatories gazing into the deepest night. It is a conflict not of politics or conquest, but of truth, a conflict between the limits of what we can see and the depths of what we can imagine. For centuries, our understanding of the universe was defined by what we could observe: stars that moved, galaxies that drifted, cosmic radiation that whispered stories from the beginning of time. But now, we have reached a strange frontier where the theories that guide us toward the origin of everything begin to split, to fracture, to turn inward upon themselves. There is no longer one clear path, but many competing visions of reality, each grounded in mathematics, each breathtaking in scope, each incompatible with the others. This is the central conflict of our time. A universe that appears infinite in size, yet may have had a singular beginning. A universe ruled by deterministic gravity, yet pulsing with quantum uncertainty. A universe we think we understand, yet cannot fully explain. At the heart of this tension is the fundamental question of whether the universe is finite or infinite. This is not simply a matter of size, it is a matter of structure, of destiny, of metaphysics. A finite universe would suggest boundaries, limits, perhaps a repeating geometry like a three-dimensional sphere, where if you traveled far enough in one direction, you would return to your starting point. Such a cosmos, while vast, is still comprehensible in principle. An infinite universe, on the other hand, is a different beast entirely. In an infinite universe, every possible arrangement of matter will occur, not just once, but countless times. There would be copies of you, of Earth, of every possible variation of every star and planet and life form. It would mean that our own existence is not unique, but one expression in a fractal of infinite permutations. And yet, the observable evidence does not tell us which of these realities we inhabit. The cosmic microwave background appears flat, but within the margin of error. The geometry of space could be infinite, or it could simply be so large that curvature cannot yet be detected. This ambiguity fuels the fire of disagreement, and the implications of either outcome are profound. Cosmologists struggle with this question not just philosophically, but mathematically. General relativity, Einstein's theory of gravity, is the backbone of modern cosmology, and it describes how matter and energy bend space and time. Its predictions have been tested with exquisite precision, from the precession of Mercury's orbit to the bending of starlight by gravity to the detection of gravitational waves. Yet when we apply it to the extreme conditions of the early universe or inside black holes, it breaks down. The equations yield singularities points of infinite density and zero volume where time stops and the laws of physics dissolve. These singularities are mathematical warnings that our understanding is incomplete. On the other side of physics lies quantum mechanics, the theory that governs the smallest scales, from electrons to quarks to the mysterious vacuum fluctuations that give rise to particles from nothing. But when we try to merge quantum mechanics with general relativity, we find chaos. Gravity refuses to quantize neatly. The equations diverge. Renormalization fails. The two most successful theories in the history of science cannot be made to speak the same language, and yet both describe essential parts of the same universe. This leads to a proliferation of theories, each seeking to reconcile the rift, each offering a different vision of the edge of the universe. String theory proposes that the fundamental building blocks of reality are not particles, but tiny vibrating strings existing in 10 or 11 dimensions. These strings can produce gravity and quantum behavior in one framework, but the theory has not yet produced testable predictions, and its landscape of possible universes is staggeringly vast. Perhaps 500 different vacuum states, each with its own physical laws. Some theorists embrace this diversity through the concept of the multiverse, an infinite ensemble of universes, each the result of inflationary bubbles branching off into separate realities. Others propose loop quantum gravity, where spacetime itself is quantized, made of discrete loops that prevent singularities and offer a possible resolution to the Big Bang paradox. Still, others look to the holographic principle, which suggests that the three-dimensional universe we observe is a projection of information encoded on a two-dimensional boundary, not unlike a cosmic simulation. These ideas are elegant, radical, and deeply unsettling. They challenge not only our conception of the universe, but the foundations of knowledge itself. Because no matter how beautiful a theory may be, it must ultimately confront the cold, indifferent voice of observation. And here too, the conflict grows. The observations we do Harvard shift data from galaxies, the uniformity of the cosmic microwave background, the distribution of large-scale structure fit beautifully with the LCDM model. A universe composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy, expanding under the rules of general relativity. This model matches the data remarkably well. And yet, it is unsatisfying. It describes what is happening, but not why. We do not know what dark matter is. We have no clue what dark energy is. The model leaves us with unanswered questions and unexplained constants, and as our data improves, cracks are beginning to appear. Recent tensions in cosmological measurements have thrown the field into deeper debate. The Hubble constant, which measures the rate of the universe's expansion, yields different values depending on how it is measured. Using the early universe's cosmic microwave background gives one result. Using supernovae and local distance indicators gives another. The discrepancy is not within the margin of error. It suggests either unknown systematic errors or new physics. This Hubble tension has ignited furious debate, with some proposing exotic new particles, others rethinking cosmic inflation, and still others challenging the very assumptions baked into our models. Similar tensions have arisen with measurements of the universe's structure, the number of neutrino species, and the behavior of dark matter in dwarf galaxies. These are not minor discrepancies, they are battle lines between competing visions of reality. At the core of all these conflicts is the human desire to define the edge, not just the boundary of space, but the limit of what we can know. Some scientists argue that the universe is inherently comprehensible, that with enough data and the right equations, we will arrive at a final theory, a cosmic blueprint that unites all forces and predicts all behavior. Others caution that we may never find such a theory, that the universe may be stranger than we can imagine, that there may be limits not just to measurement, but to human cognition itself. Gödel's incompleteness theorems show that even in mathematics, some truths are forever beyond proof. Quantum uncertainty means that some events have no cause, only probability. The anthropic principle, which suggests we observe the universe we do because only such a universe can support observers, flirts with tautology, and tests the boundary between science and philosophy. And yet, in the midst of this conflict, cosmology thrives. Because tension is not paralysis, it is energy. It is the creative force that drives science forward, that demands new experiments, that invites bold ideas and sharp critiques. It is the recognition that truth is not a fixed point, but a horizon that shifts as we move. In the deepest sense, the conflict in cosmology is a reflection of a deeper human paradox. We are creatures of finite size and lifespan, gazing into an infinite and ancient cosmos. We seek final answers in a world of eternal questions. We long for closure in a universe that may offer only complexity. Still, we press on. We build new telescopes to peer further into the past. We send probes to the outer planets and beyond. We develop quantum computers to simulate the origin of space-time. We refine our models, challenge our assumptions, and prepare for the unexpected. Because the conflict is not a sign of failure, it is the pulse of discovery. It means we have reached the edge of what we know, and beyond that edge lies not despair, but possibility. The possibility that the universe is not only stranger than we imagine, but stranger than we can imagine. And that perhaps is the greatest truth of all. That in the clash of ideas, the universe reveals not just its secrets, but its power to transform us, to humble us, and to lift our minds toward the infinite. If the universe has no edge, then our place in our very way of thinking about space, time, and reality must be reimagined from the ground up. Not just metaphorically, not just poetically, but fundamentally, because the absence of an edge means the absence of finality, no boundary to define what's inside or outside, no perimeter to cross, no wall to reach. It means that every line of thought that assumed an ultimate frame of reference, of space, of origin, must be re-examined. The consequences of this conflict, between a universe with definable limits and one that stretches forever in all directions, are not abstract. They strike at the heart of physics, cosmology, and human thought. Because an edgeless universe doesn't simply expand, it destabilizes. It challenges the very notion of containment. It dissolves categories we once trusted, beginning and end, center and periphery, known and unknown. For physicists, the implications are profound. If the universe has no edge, then any attempt to understand it as a thing in the traditional sense collapses. We cannot map it like a terrain, cannot treat it as an object suspended in a greater nothing. The idea of a boundary requires a distinction between what is and what is not, between the cosmos and something else. But if there is no edge, then there is only is. Reality becomes the totality of all things, with no outside to compare it to. That destroys classical intuition, because every theory we have about motion, energy, and causality is built on frame spaces defined by their limits. Newton's laws worked in bounded systems. Einstein extended those laws to curved space, but always with implicit borders in mind: the observable region, the local geometry, the gravitational well. But in an infinite, edgeless universe, we can no longer talk meaningfully about the rest of the universe, or about any definitive whole. The idea of total energy, total mass, total entropy, all of it, becomes questionable. Conservation laws, so fundamental to physics, may break down over cosmic distances. Our best models may only apply locally, within regions small enough to be considered semi-isolated, while the grand structure remains beyond formulation. In cosmology, this changes the rules of engagement. The observable universe is already limited by the speed of light and the age of space. But if the universe is infinite and edgeless, then the observable region is just a speck of bubble in an endless foam of existence. That alone raises uncomfortable questions. Is what we observe typical? Are the laws of physics constant everywhere? The cosmological principle assumes so that the universe is homogeneous and isotropic on large scales, but we only have access to one bubble, one vantage point. If space goes on forever, there may be regions where gravity behaves differently, where matter clumps in strange patterns, where even the constants of physics like the speed of light or the strength of the strong nuclear force vary. In such a universe, cosmology becomes not the study of everything, but the study of one local patch. That forces humility. It demands we treat our models not as absolute, but as provisional, as conditioned by perspective. It opens the door to theories that rely not on universal laws, but on selection, affects anthropic reasoning. The idea that we observe this universe not because it is the universe, but because it is one of many that can support observers like us. This undermines the dream of a single, elegant theory of everything. It suggests that some features of our cosmos are accidents of cosmic geography, not necessities of logic. And if that's true, if the universe has no edge and may vary endlessly in space and form, then the need for new physics becomes urgent. Not just better versions of what we have, but radically different approaches that abandon assumptions we've held for centuries. General relativity assumes a smooth, continuous fabric of space and time, but quantum mechanics teaches us that reality at its deepest level is discrete, probabilistic, governed by uncertainty. Attempts to unify these theories have led to string theory, loop, quantum gravity, and other exotic frameworks, but none have yet resolved the conflict. An infinite, edgeless universe would require a theory that operates without background structure, without fixed scales, without global boundaries. It might require us to treat space-time itself as emergent, not fundamental arising from networks of entanglement, from topological information, or from deep symmetries we haven't yet discovered. Time itself may not be absolute, but a derived property of quantum correlations. Space may be a manifestation of information flow, not a container. In such a view, the edge isn't missensit, never existed. The universe wasn't created in space, it created space. But the implications don't stop with physics. If the universe has no edge, what does that mean for us fragile creatures on a speck of dust, looking out into the dark? It means the Earth is not just small, it is infinitely small, one of countless places in an unbounded sea of possibility. That may inspire awe, but it also invites existential vertigo. What does it mean to matter in an infinite universe? If every possible version of you exists somewhere, if every permutation of life and history plays out in distant, unreachable regions, does that render our choices meaningless? Does it collapse identity into statistical noise? Or does it mean the opposite, that the uniqueness of our local perspective is the only thing we can truly trust? In an infinite universe, there is no privileged frame, no cosmic center, no ultimate point of reference. There is only here and now. That can be terrifying. It can also be liberating. It means that meaning is not given, it must be made. That consciousness, however brief and limited, is a candle in the dark. And that the dark, no matter how infinite, cannot extinguish the light that arises within it. Philosophically, an edgeless universe forces us to confront the limits of explanation. If there is no outside, then there can be no external cause. If there is no boundary, there can be no beginning in space. If the universe is eternal and infinite, it may have no reason, only process. That undercuts traditional notions of causality, of teleology, of divine architecture. It makes the question, why is there something rather than nothing? Harder to answer because it assumes that nothingness is the default, the natural state. But what if it isn't? What if existence is the default, and nothingness is the anomaly? What if the universe is not a thing created, but a process unfolding, with no start or end, no creator or conclusion, only becoming? These are not answers science can easily give, but they are questions it inevitably raises. They connect physics to metaphysics, cosmology to meaning. The absence of an edge also reframes our relationship with the unknown. If there is no edge to the universe, then there is no edge to inquiry. Every discovery opens more questions. Every explanation leads to deeper mysteries. There is no final theory, only better approximations. That is both frustrating and beautiful. It means that science is not a ladder to a final truth, but a lantern in the foggalways, revealing, never completing. It means that humility is not just a virtue, but a method. That wonder is not weakness, but strength. It reminds us that knowledge is not a place to arrive, but a direction to walk. And that the universe, in all its edgeless expanse, is not just a backdrop for our lives, it is a mirror, showing us who we are and who we might become. And so, the consequences of the conflict are not just technical, they are emotional, existential, civilizational. A universe with no edge invites not despair, but responsibility. It means that our choices, our cultures, our dreams happen in a context that is infinitely vast and utterly indifferent. But that indifference does not diminish their value, it heightens it. Because in a universe with no end, meaning is not imposited, is created, not once, but constantly, not universally, but locally. And that creation is our greatest gift. In the face of an infinite cosmos, we build instruments to see farther, equations to think deeper, stories to bind us, and questions to keep us human. The universe may have no edge, but we do. We are the edge of thought, of awareness, of becoming. And in embracing that, we begin to understand that the true consequence of the conflict is not defeat, but transformation. We do not need the universe to end to make our lives meaningful. We only need the courage to live, to wonder, and to reach endlessly. The story of the universe changed forever when we learned it wasn't slowing down, it was speeding up. For decades, cosmologists assumed that gravity would eventually overcome the momentum of the Big Bang. The only question was how. Would the universe expand forever, gradually slowing but never stopping? Or would it halt and collapse in a big crunch, reversing time's arrow? But in 1998, two independent teams of astronomers, led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, looked deep into the cosmos and found something no one expected. By studying Type Ia supernova stellar explosions that act as cosmic mile markers, they discovered that distant galaxies weren't just far away, they were farther than they should have been. The expansion of the universe was not decelerating, it was accelerating. Something unseen, some force or field, was pushing the cosmos apart at an ever-increasing rate. This revelation was more than a data point. It was a rupture in the foundation of modern cosmology, and it marked the turning point in our understanding of the universe. That force was soon named dark energy, though the term explained nothing. It accounted for nearly 70% of the energy density of the universe, yet it had never been detected directly. It did not cluster like matter, did not emit radiation, and could not be felt or measured except through its effect on expansion. Its properties were inferred by comparing the redshift of light from distant objects to their intrinsic brightness. But its impact was enormous. Enormous, in fact, that dark energy now dominates the fate of the cosmos. If its strength remains constant, galaxies will drift ever farther apart, stars will die out, and the universe will end not in fire or collapse, but in darkness, a cold, empty silence known as the heat death. If dark energy changes over time, the fate may shift. It might fade, causing gravity to reassert itself. Or it might grow stronger, tearing galaxies, stars, planets, and even atoms apart in a catastrophic Big Rip. Either way, the discovery of cosmic acceleration was not just a new chapter in cosmology, it was a new book entirely. But it wasn't the only breakthrough reshaping our view. Around the same time, the cosmic microwave background, the faint afterglow of the Big Bang, was being mapped with unprecedented precision. First, by COBE in the 1990s, then by WMAP in the early 2000s, and finally by Planck, launched in 2009. These space telescopes captured the oldest light in the universe, revealing tiny fluctuations in temperature and density, echoes of quantum irregularities stretched across space by inflation. These fluctuations became the seeds of galaxies, stars, and planets. By measuring them, scientists could reconstruct the early universe with incredible accuracy. They determined its age, 13.8 billion years, its composition, 5% normal matter, 27% dark matter, 68% dark energy, and its geometry, flat to within a fraction of a percent. This wasn't just date, it was a cosmic fingerprint, a snapshot of the infant universe, frozen in time, carrying the imprints of the forces that shaped everything that followed. Then came gravitational waves, predicted by Einstein in 1916. They were long considered undetectable. But in 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, changed that forever. Twin observatories in Washington and Louisiana recorded the ripples in space-time caused by the merger of two black holes over 1 billion light-years away. The signal lasted a fraction of a second, but it confirmed a key prediction of general relativity and opened a new window on the cosmos. Unlike light, which can be blocked or scattered, gravitational waves pass through matter untouched. They allow us to observe the universe in a fundamentally different way, not through what we see, but through what we feel, as space-time itself stretches and contracts. Since that first detection, dozens more have followed, from black hole mergers to neutron star collisions. These events don't just confirm theories, they reveal things we never knew to ask. One neutron star merger created heavy elements like gold and platinum, solving a long-standing mystery about the origin of the periodic table's heaviest atoms. Another offered a new way to measure the Hubble constant, helping to resolve the growing tension between early and late universe expansion rates. Meanwhile, another revolution was quietly unfolding: the discovery of exoplanets. Before 1995, the only planets we knew of orbited our Sun. Now we know of thousands, thanks to space telescopes like Kepler, TESS, and the James Webb Space Telescope. Kepler stared at a patch of sky and watched for tiny dips in starlight as planets passed in front of their stars. TESS scanned the entire sky, finding candidates everywhere. And James Webb, with its massive infrared mirror, is now peering into the atmospheres of these worlds, searching for signs of water, oxygen, methane ebiosignatures that might hint at life. These planets come in every size and configuration imaginable. Hot Jupiters skimming the surfaces of their stars, rocky super-Earths in habitable zones. Systems with 7 Earth-sized planets packed tightly around cool red dwarfs. The idea that Earth is unicon central to our worldview is now untenable. We live in a galaxy, teeming with worlds, in a universe where planets may outnumber stars, and that changes everything. Because if life emerged here, it may have emerged elsewhere. And if it did, the search for meaning is no longer ours alone. All of this, the discovery of dark energy, the precision mapping of the early universe, the detection of gravitational waves, the census of exoplanets represents a turning point not just in our knowledge, but in the way we ask questions. We no longer live in a cosmos defined by the limits of our sight. We have machines that see in microwaves, X-rays, infrared, ultraviolet, and gravitational waves. We have software that finds patterns in noise, simulations that model the birth of galaxies, and theories that stretch to the edge of imagination. We are no longer passive observers of the stars, we are active participants in decoding their message. And the message is clear. The universe is stranger, older, and more beautiful than we ever imagined. But this turning point is not a resolution, it is a rupture. The more we learn, the more we see the edges of our ignorance. Dark matter discovered through its gravitational pull on galaxies remains invisible and mysterious. Is it a particle? A field? A symptom of modified gravity? We don't know. Dark energy, the engine of cosmic acceleration, is even more elusive. It may be a property of space itself, a new quantum field, or an illusion born of our misunderstanding of gravity. String theory and loop quantum gravity offer possible unifications of physics, but remain untested. The multiverse, a natural outcome of eternal inflation, offers explanation without prediction. And the Hubble tension the discrepancy between different methods of measuring cosmic expansion hints that something fundamental may be missing from our model. Perhaps we are on the verge of another paradigm shift, like those of Copernicus, Newton, and Einstein. Or perhaps we are approaching the limits of human knowledge, where further progress requires not just new data, but new minds, new tools, new ways of thinking. Technologically, we stand on the threshold of even greater discoveries. The James Webb Space Telescope is just beginning its mission, already revealing ancient galaxies too massive and structured for current models to explain. The Nancy Grace Roman Space Telescope will survey wide areas of sky with high precision, probing dark energy and dark matter through gravitational lensing. The Vera Rubin Observatory will create a time-lapse of the sky, discovering transients, mapping structure, and possibly detecting new types of objects. Next-generation gravitational wave detectors like LISA will hear lower frequencies, including signals from supermassive black hole mergers. And particle physicists are designing new accelerators, new detectors, and quantum sensors to probe the fundamental nature of reality. Artificial intelligence is revolutionizing data analysis, finding patterns that humans miss, identifying exoplanets, refining simulations, and even helping formulate new hypotheses. This is the era we live in, one of questions that bend reality, of instruments that see the invisible, of theories that flirt with the infinite. The turning point is not just scientific, it is existential. We now know we are not the center of the universe, not the sole owners of life, not even in possession of final truth. We are fragments of a cosmic process, born in the depths of stars, caught in the dance of expansion, surrounded by silence we are just beginning to decode. And yet, we are decoding it. Slowly, painfully, brilliantly. With every photon we catch, every wave we feel, every equation we write, we step further into the unknown. This is not the end of the story. It is the turning of the page. The moment when the universe stops being a backdrop and becomes a character. The moment when observation becomes participation. When the cold facts of science become the hot embers of awe. Because to know that the universe is expanding, accelerating, whispering in gravitational waves, hiding dark matter, seeding life on distant planets really know that is to stand in the presence of something sacred. Not in the religious sense, but in the human one. Sacred because it humbles us. Sacred because it connects us. Sacred because it means that we, brief flickers of awareness on a small planet orbiting a mediocre star, are able to look up, ask questions, and understand. Not all, but enough. Enough to see that the universe is not a puzzle to be solved, but a mystery to be embraced. And in that embrace, we turn not away from ignorance, but toward possibility. Toward a future where the unknown is not feared, but welcomed. Where the limits of today become the revelations of tomorrow. And where the story of the cosmos, once thought distant and cold, becomes our own. What if the problem isn't the universe, but how we're looking at it? What if all our struggles to define its boundaries, to unify its laws, to reconcile the contradictions between general relativity and quantum mechanics arise not from the cosmos itself, but from the limitations of our perspective? For centuries, we've interpreted the universe through the lens of our senses, our mathematics, and our metaphor space, as a stage, time as a river, gravity as a force, particles as tiny billiard balls. But as we peer deeper into the quantum realm and stretch our minds to the scale of the cosmos, those metaphors begin to crumble. Our models, once so elegant and complete, begin to twist under the weight of their assumptions. We find ourselves trapped in paradoxes, black holes that erase information, particles that exist in two places at once, space that bends and expands faster than light, entanglement that defies distance. These are not quirks, they are signs. Signals that our old mental frameworks are breaking down and that we may be asking the wrong questions altogether. This is where the shift begins. The realization that reality may not be what it seems, and that the cosmos might not be a vast three-dimensional expanse, but something far more subtle and strange. Among the most radical of these new ideas is the holographic principle, a concept that challenges the very foundation of how we think about space and information. Originally proposed in the 1990s by physicists Gerard Hooft and Leonard Susskind, the holographic principle emerged from the study of black holes and their thermodynamic behavior. According to general relativity, a black hole's entropy measure of its disorder or information content is proportional not to its volume, as one might expect, but to the area of its event horizon. This startling result suggests that all the information contained within a region of space can be encoded on its boundary surface, just as a hologram stores a three-dimensional image on a two-dimensional film. If this holds true not just for black holes, but for the universe as a whole, then everything we experience as space, time, matter, energy might be a projection of quantum information inscribed on a distant, lower dimensional boundary. In other words, the inside of the universe might be an illusion, a kind of emergent reality generated from data that lives elsewhere. This isn't just science fiction. It finds mathematical expression in string theory, particularly in the ADS CFT correspondence developed by Juan Maldacena in 1997. This duality shows that a theory of gravity in a higher dimensional bulk space can be equivalent to a quantum field theory on its lower dimensional boundary, without gravity. The implications are enormous. Gravity may not be fundamental, but emergent. Space and time may be the result of entanglement patterns in quantum fields. The universe may be, in a deep and literal sense, informational. This viewpoint upends centuries of thinking. No longer is space the container in which matter moves. Instead, space may emerge from the relationships between quantum qubits entangled across a network that has no intrinsic geometry, only correlation. Time, too, may be an emergent property of change in those relationships. We are not moving through space-time. We are made of space-time. And space-time is made of information. This shift in perspective isn't just theoretical. It reshapes how we approach the deepest puzzles in physics. Take the black hole information paradox. If a black hole evaporates through Hawking radiation, what happens to the information about the particles that fell in? If it's lost, quantum mechanics is violated. If it's preserved, then general relativity must break down. The holographic principle offers a solution. The information isn't lost, it's encoded on the event horizon and slowly released in the radiation, albeit in a scrambled form. This resolves the paradox without violating either theory. But it also implies that our usual notions of locality of things happening here rather than there may be illusions. What appears to happen inside the black hole is already encoded on its surface. What appears to happen in our universe may be encoded elsewhere entirely. This non-locality challenges the very foundation of scientific explanation. How can we talk about causality, about events, about trajectories, if the space in which they occur is itself an emergent illusion? And yet, this is not a defeat. It is a revolution that quantum mechanics has been hinting at for over a century. From the double-slit experiment to Schrödinger's cat, quantum physics has always defied classical intuition. Particles behave like waves. Observation affects reality. Entanglement links particles across cosmic distances. These aren't just oddities, they are clues. They tell us that reality is not made of solid, definite things, but of probabilities, of relationships, of potentialities that only resolve when measured. The universe is not a machine, but a process. And quantum mechanics is not just a set of rules for small things. It may be the operating system of the entire cosmos. This idea gained support from recent attempts to describe the fabric of spacetime in quantum terms. In loop quantum gravity, space is not continuous but quantized, built from loops of abstract geometry. In causal set theory, spacetime is a network of discrete events linked by cause and effect. In tensor networks, spacetime geometry emerges from patterns of quantum entanglement. These approaches differ in detail, but share a common thread. They treat space and time not as background arenas, but as emergent phenomena, arising from something deeper. In this view, the universe is not a stage, but a story and narrative of evolving relationships, written in the language of quantum information. This shift also changes how scientists talk to each other. The old divisions between quantum and classical, particle and wave, space and time begin to dissolve. New collaborations emerge, crossing the boundaries of disciplines. Physicists working with information theorists, computer scientists with cosmologists, philosophers with mathematicians. Concepts like entropy, computation, and complexity begin to take center stage, not as metaphors, but as the fundamental building blocks of physical reality. Debates grow more open-ended. What is real? What is fundamental? Can a simulation be conscious? Is the multiverse science? These are no longer fringe questions. They are the frontier. The impact of this shift extends beyond science. It touches philosophy, metaphysics, even theology. If reality is a projection, what is it projected from? If the laws of physics emerge from information, where does that information reside? Is there a cosmic code, and if so, what wrote it? These questions don't demand answers, but they demand attention. they invite a broader dialogue between science and the humanities, between facts and meaning. They remind us that the pursuit of knowledge is not just a technical task, but a human 1EA quest for understanding in a universe that may never fully yield its secrets. Yet for all its strangeness, the shift in perspective is also deeply grounded in experience. We are already holograms in a sense. Our brains do not see the world directly. They receive signals, photons, vibrations, chemical sand reconstruct a model of reality. That model is not the world itself, but an internal simulation. We live in that simulation every day. The idea that the universe itself might work similarly is not alien, it is intimate. We are not outside observers. We are participants in the code, loops in the story, patterns in the weave. Our thoughts, our dreams, our questions, they are not exceptions to the laws of nature. They are the laws expressed at the level of consciousness. And so, the question is not just, what is the universe made of, but what is it for? Not in the teleological sense, but in the informational one. What does it compute? What does it express? What kind of being produces a reality where observation matters, where entanglement defines structure, where geometry is born of relationship? Perhaps the shift in perspective is not just about physics. Perhaps it is about awakening, realizing that the universe is not something we look at, but something we look through, and something that looks through us. Perhaps reality is not a place to be explained, but a song to be sung, a pattern to be danced, a mystery to be lived. This does not mean abandoning rigor. Quite the opposite. The new physics demands greater precision, deeper mathematics, more careful logic. But it also demands imagination, the courage to let go of old certainties and embrace new paradigms. The shift in perspective is not a rejection of science. It is science at its best. Bold, humble, creative, and open to wonder. It is a reminder that the universe is not obliged to fit our expectations. It is what it is. And our task is to listen, to explore, to model, to askand above all, to keep asking, even when the answers change the questions. Because in the end, the shift in perspective is not just about black holes or holograms. It is about us. About how we choose to understand our place in a universe that may be stranger than fiction, deeper than thought, and more beautiful than we can yet imagine. It is about opening the door to a future where knowledge is not the end of mystery, but its beginning. And in that future, we may find not just new theories, but new ways of being, new ways of seeing the same stars, and realizing they were never far away. They were always within us, coded in light, waiting to be seen. It was supposed to be simpler, at least simpler. The universe, once imagined as an infinite expanse filled with stars scattered across a void, was slowly brought under the reign of scientific law. Newton's gravity, Einstein's relativity, the expanding cosmos of Hubble. For generations, physicists refined the rules, built better models, and expanded their reach, mapping galaxies, decoding the afterglow of the Big Bang, charting the motion of dark matter's hidden hand. The story seemed to be converging toward elegancy, a final theory, a cosmic blueprint, a unifying explanation that would reveal the architecture of reality. But just as everything appeared to align, something strange began to happen. Discoveries emerged not quietly, but explosively, that didn't just add new chapters to the book of the cosmos. They ripped out entire sections. They suggested that perhaps the rules themselves were wrong, or incomplete, or local to only one version of reality. This was the unexpected twist, the realization that the universe might not be a universe at all, but part of something far stranger, a multiverse, a simulation, a quantum fluctuation in an ocean of eternities. And with that came a deeper and more profound shift in consciousness, that we may never find the edge of the universe, not because it lies too far away, but because it doesn't exist in the way we think. Perhaps the edge lies within, in the limits of perception, of assumption, of imagination itself. The first cracks in the classical picture came not from mysticism or philosophy, but from data, real, solid, measurable anomalies that couldn't be explained by existing theories. Take the discovery of supermassive black holes in young galaxy objects, so vast, so dense, that their formation in the short time after the Big Bang seemed impossible under conventional models, or the detection of galaxies that appeared too mature, too well structured, too soon in the timeline of cosmic evolution. Observations made by the James Webb Space Telescope showed massive, dust-rich galaxies already formed less than 500 million years after the Big Bang, a result that confounded standard models of galaxy formation and suggested that something fundamental was missing from our picture of early structure growth. Then came the tension in measurements of the Hubble constant, the rate of cosmic expansion, where two different methods, one based on the early universe via the cosmic microwave background, and the other on the local universe via supernovae and variable stars, yielded results that stubbornly refused to align. This wasn't a mere technical discrepancy. It pointed to the possibility that our cosmological model, the so-called lambda CDM framework, might be incomplete or even fundamentally flawed. In response, theorists turned to bold ideas none bolder than the multiverse. At first glance, it seems like fantasy. Countless universes, each with different physical laws, branching infinitely in space or time. But the multiverse is not an invention of science fiction. It arises naturally from several of our most successful theories. Inflationary cosmology, which describes the exponential expansion of space in the first fraction of a second after the Big Bang, predicts that this inflation never truly ends. Instead, in many models, it creates pocket universes, each emerging from a bubble of inflation that stops locally while the background space continues inflating. Each bubble is a universe unto itself, potentially with different parameters, different particle masses, constants, or even dimensional structures. In string theory, which posits that the fundamental constituents of the universe are not particles but vibrating strings in 10 or 11 dimensions, there are estimated to be 10,500 possible vacuum states, each corresponding to a different way of compactifying extra dimensions. This landscape of solutions suggests that our universe might be one of many, selected not by necessity but by chance. The implications of the multiverse are staggering. It means that everything we consider fundamental or laws of physics, the structure of matter, the strength of gravity, might be local accidents. In other universes, stars might not form, atoms might not hold together, time might flow backward, or not at all. And yet, here we are, in a universe that just so happens to support complexity, chemistry, consciousness. The anthropic principle, once dismissed as philosophical hand-waving, gains unexpected relevance. We observe this universe because it is the one where observers can exist. This doesn't satisfy everyone. Some see it as a retreat from predictive science, replacing explanation with selection bias. But others see it as a new frontier that reframes the question from "why is the universe this way?" to "what kinds of universes are possible, and why are we in this one?" And if that weren't strange enough, another possibility emerged, one with even more unsettling consequences: the simulation hypothesis. First proposed in rigorous form by philosopher Nick Bostrom in 2003, the idea is disarmingly simple. If it is possible to simulate conscious beings inside a computer, and if a civilization advances to the point where it can run many such simulations, then simulated realities would vastly outnumber base realities. Therefore, statistically speaking, it is more likely that we are living in one of the simulations than in the original universe. This idea, once considered fringe, gained traction among serious thinkers. Physicist Seth Lloyd and others pointed out that the universe behaves suspiciously like a computational system, governed by quantized energy levels, discrete symmetries, and finite information density. Theoretical work in quantum gravity, particularly the ADS-CFT correspondence, suggests that reality might be a projection of lower-dimensional data digital construct rather than a continuous analog field. Even anomalies in cosmic background radiation and particle behavior have been investigated as potential glitches in a simulated matrix. This doesn't mean we live in a video game. It doesn't mean there's a keyboard somewhere or that someone is watching us. But it does raise profound questions about what it means for something to be real. If our reality is a simulation, then so long as the rules remain consistent, our experience is valid. The physics works. The emotions matter. But it also means that reality could be altered, stopped, or deleted. That there may be levels of causality beyond what we can detect. That what we call the universe might be embedded in a deeper substratian informational domain, where what matters is not space or matter, but data and code. In this view, physical laws are like programming logic, and quantum events are computations. And we, conscious agents, are emergent phenomena of this cosmic software. Such ideas might seem speculative, but they reflect a broader trend, the shift from seeing reality as stuff to seeing it as information. Quantum mechanics already treats systems not as solid objects, but as wave functions, mathematical descriptions of probabilities. Entropy, once a thermodynamic concept, is now a measure of information content. Black hole physics shows that information is conserved even in extreme conditions, and quantum entanglement, long dismissed as spooky action at a distance, now appears to be the glue that holds space-time together. As physicist Eric Verlinde proposes, gravity itself might not be a force, but an emergent effect of entropic gradients in information fields. Space, time, and matter might be the shadows of a deeper reality, one where the fabric of existence is woven from bits and logic. This is the twist, that what we thought was fundamental, the galaxies, the stars, the atomsis, not. That what we cannot see, the information, the fields, the patterns, is more real than the matter it shapes. This doesn't make the universe less meaningful. It makes it more mysterious. It means that behind the curtain of physical reality lies a deeper structure, one that is mathematical, relational, and possibly conscious. Because if information is fundamental, and if consciousness is a process of integrated information as proposed by theories like integrated information theory, then awareness may not be an accident of biology. It may be an intrinsic property of the cosmos. Perhaps the universe doesn't just contain observers. Perhaps it is, in some sense, observing itself. This realization changes everything. It means we are not separate from the universe, but expressions of it, not anomalies in a dead mechanism, but nodes in a living network. It means that the most important questions are not, what is the universe made of? But what is its structure? What are its rules? What patterns give rise to meaning? And it means that the search for the edge, for a final boundary, a stopping point, a complete map, may be a misunderstanding. There is no edge. There is only emergence, only deeper levels of structure, each one giving rise to the next, like nested algorithms or unfolding stories. So where does that leave us? It leaves us humbled, certainly, but also empowered. Because even in a multiverse, even in a simulation, even in a holographic information-based cosmos, we matter. Our questions matter. Our curiosity is not a trivial impulse. It is the universe's way of evolving, of becoming more self-aware. The twist is not that reality is less real than we thought. The twist is that it is more layered, more dynamic, more alive. And the edge we've been searching for? It's not out there. It's the point at which we stop asking questions, which means the true edge of the universe is curiosity itself. So long as we keep reaching, keep wondering, keep listening, the story continues, and the cosmos, whatever its origin, continues with us. The universe has given up many of its secrets, but not all. For every stunning breakthrough in cosmology and physics, there emerge a dozen new puzzles, deeper questions that refuse easy answers. We've mapped the cosmic microwave background, detected gravitational waves, glimpsed galaxies from the infant universe, and watched black holes collide across billions of light years. And yet, the most important pieces of the cosmic puzzle remain missing. We don't know what 95% of the universe is made of. We don't understand the nature of time or the true origins of space. We don't know how to unify the large and the small, the smooth geometry of general relativity and the jittery probabilities of quantum mechanics. We are standing on the edge of an intellectual frontier, and while the view is grand, the road ahead is rough. The universe is calling us forward, but it won't yield its deepest truths without a fight. These are the new challenges, technical, theoretical, philosophical, and they will define the next century of exploration. The most immediate challenge is observational. As powerful as our instruments are, they are still crude compared to the scale and subtlety of the phenomena we're trying to detect. Our most distant observations are still bound by the cosmic light horizon, a limit imposed by the speed of light and the finite age of the universe. We cannot see beyond the surface of last scattering, the boundary where the universe became transparent 380 years after the Big Bang. Beyond that lies an opaque era of plasma and fire, inaccessible to electromagnetic radiation. This barrier isn't just practical, it's physical. Light cannot carry information from that realm. We need other messengers, neutrinos, gravitational waves, perhaps exotic particles yet undiscovered. But detecting such signals requires sensitivity orders of magnitude beyond what we currently possess. Even within the visible universe, our reach is limited. The James Webb Space Telescope has pushed our view deeper into time, revealing galaxies just 300 million years after the Big Bang. But even it struggles to detect faint, low-mass structures at those distances. The earliest phases of galaxy and star formation remain cloaked in mystery. We cannot yet resolve the moment when matter began to organize into the structures we see today. We cannot observe the formation of the first black holes, or the transition from primordial gas to stellar light. These are not minor details. They are foundational epics, the missing pages of our origin story. Closer to home, our understanding of dark matter remains crippled by its invisibility. We know it exists because of its gravitational effects in galactic rotation curves, lensing, structure formation. But every attempt to detect it directly has failed. Decades of underground detectors have yielded no confirmed particles. Proposed candidates like WIMPs, weakly interacting massive particles, and axions remain elusive. Alternative models, like sterile neutrinos or modifications to gravity, have yet to produce conclusive results. Without a direct detection, we are left inferring properties from shadows, measuring effects, not substance. It's like trying to understand a windstorm from the way trees bend, without ever feeling the wind itself. Dark energy presents an even greater mystery. Its presence is inferred from the acceleration of cosmic expansion, but its identity remains unknown. Is it a cosmological, constantin inherent property of space? Or a dynamic field that evolves over time? Could it decay, intensify, or interact with matter? Our current data are insufficient to distinguish between models. Future missions like the Nancy Grace Roman Space Telescope and the European Space Agency's Euclid Observatory aim to map cosmic expansion with greater precision. But they will only take us so far. To truly understand dark energy, we may need new physics, new frameworks that go beyond general relativity, quantum field theory, or even the standard assumptions about the fabric of space. Technologically, we face daunting engineering challenges. Building bigger telescopes means confronting the limits of material science, cryogenics, and orbital mechanics. Ground-based observatories must contend with atmospheric distortion, while space telescopes must survive harsh environments and remain stable for decades. The upcoming Extremely Large Telescope, ELT, in Chile, will use adaptive optics to correct for atmospheric blur. But even it cannot see in certain infrared and microwave bands without space-based support. Coordinating multi-wavelength, multi-messenger astronomy requires global networks, synchronized instrumentation, and data processing on a scale never before attempted. In particle physics, the situation is equally complex. The Large Hadron Collider, LHC, has confirmed the Higgs boson but has failed to uncover supersymmetry or any of the other new physics predicted to lie beyond the standard model. We are approaching the energy limits of terrestrial accelerators. To go further, we may need colliders the size of cities or entirely new concepts, like muon colliders or plasma Wakefield accelerators. Each comes with its own technical and financial barriers. Meanwhile, precision experiments in atomic physics, cosmology, and quantum information offer new routes to discovery, but demand unprecedented levels of accuracy and stability. And then there is the theoretical bottleneck. Our equations work, but only separately. General relativity describes gravity, space, and time on large scales with astonishing precision. Quantum field theory describes the behavior of particles, forces, and fields at the smallest scales with equal success. But the two cannot be reconciled. Attempts to unify them into a theory of quantum gravity string theory loop quantum gravity, causal dynamical triangulations, holographic duality remain incomplete. Each offers insights, but none are complete or testable. The mathematics is daunting. The conceptual challenges are worse. What does it mean to quantize spacetime? Is time itself fundamental or emergent? What is the role of the observer in a theory of everything? Cosmologists must also grapple with deep ambiguities about the nature of the universe itself. Is it infinite or finite? Is it closed, open, or flat? Does it repeat? Was there a time before the Big Bang? Is our universe one of many, in a vast multiverse shaped by inflation or string theory? These questions are not merely speculative. They affect how we interpret data, how we model early structure, how we calculate probabilities. Yet many of them may lie forever beyond our observational reach. If the multiverse is real, we may never detect the other universes. If cosmic inflation extends beyond our horizon, we cannot confirm it directly. We are trapped in a causal bubble, observing only a tiny patch of a potentially vast and unknowable whole. Still, scientists are not deterred. They are mapping out bold strategies for tackling these challenges. New generations of observatories will peer deeper and wider. The Rubin Observatory will survey the sky in motion, detecting transients, asteroids, and supernovae with unprecedented speed. The Roman telescope will measure the geometry of space, the distribution of galaxies, and the fingerprints of dark energy. The Event Horizon Telescope will refine its view of black hole shadows. New CMB experiments, CMB-S4, Lightbird will hunt for the imprint of primordial gravitational waves, testing inflation and cosmic origins. Space-based interferometers like LISA will detect gravitational waves from supermassive black holes, compact binaries, and perhaps exotic objects like cosmic strings or dark matter clumps. Meanwhile, theorists are working to reformulate the questions. Instead of asking what space-time is, they ask how it arises. Instead of assuming unification, they explore emergence. Quantum information theory, long a niche field, is now central to understanding black holes, entropy, and entanglement. The idea that space arises from entangled states pioneered by the holographic principles being tested in simulations, tensor networks, and condensed matter analogs. Mathematicians are building new geometric frameworks to model quantum space-time. Philosophers and physicists alike are revisiting the nature of time, causality, and reality. The role of computation is also expanding. Artificial intelligence is being used to analyze telescope data, simulate galaxy formation, optimize detector configurations, and even generate new hypotheses. Machine learning models can find patterns in data that would take humans decades to see. Quantum computing, still in its infancy, promises to model quantum systems that classical computers cannot. As these tools mature, they will become essential to the next phase of discovery, not just amplifying human capacity, but extending it into domains previously unreachable. At the same time, interdisciplinary collaboration is growing. Cosmologists talk to string theorists, particle physicists to computer scientists, philosophers to engineers. Boundaries between fields are dissolving. Questions like, what is dark energy? Or, what came before the Big Bang? Can no longer be answered from a single discipline. They require a synthesis of ideas: mathematical, experimental, conceptual. They demand new languages, new metaphors, new modes of thought. Education must evolve too. The next generation of scientists will need to think not just deeply, but broadly. They will need to master complexity, tolerate ambiguity, and navigate a landscape where even the definitions of time, space, and matter are in flux. And above all, scientists must remain open to surprise. The universe has fooled us before. It may do so again. The next great discovery may not come from a billion-dollar telescope or a 10-year simulation. It may come from an unexpected anomaly, a stray photon, a mathematical curiosity. That is the nature of frontier science. It is not linear. It does not proceed by adding bricks to a wall. It leaps, stumbles, doubles back. It is shaped by uncertainty, by failure, by wonder. But each step forward expands the horizon of what is knowable. Each new challenge opens a door to deeper understanding. So what lies ahead? a universe still shrouded in mystery but no longer silent. We are beginning to hear its voice in waves of gravity, in patterns of light, in quantum whispers and cosmic rhythms. We are beginning to see it not as a machine, but as a living code-structured, evolving, emergent. The challenges are immense, but so is the potential. We may never find all the answers, but in asking the questions, we become more than observers. We become participants in the unfolding of the cosmos, not because we control it, but because we listen, we learn, and we never stop reaching. That is the promise of the next century of science. Not certainty, but connection. Not mastery, but understanding. Not the end of mystery, but its transformation into meaning. The universe is waiting. And the next chapter is ours to write. At the highest levels of science, a storm is brewing, not of chaos, but of fierce and brilliant minds racing toward a singular goal: the unification of the cosmos. The final confrontation in cosmology is not a battle with weapons or territory, but with ideas, with equations, with questions that do not yield easily to answers. On one side, we have the elegant sweep of general relativity, Einstein's masterwork, which describes how mass and energy shape the fabric of space-time itself, predicting black holes, gravitational waves, and the bending of light across cosmic gulfs. On the other side stands the quantum world, governed by probabilities and wave functions, where particles blink into and out of existence, and nothing is certain until observed. Both theories are deeply successful in their own domains, but at their borders inside black holes, at the moment of the Big Bang, in the first instance of the universe's birth, they clash. They become incompatible, and the contradiction threatens to tear apart our picture of the cosmos. To resolve this, to find the true architecture of reality, to answer whether the universe has a boundary or whether it loops, stretches, or infinitely expands. This is the confrontation at the heart of modern physics, and it is unfolding now. There are several competing theories in play, each with its own promises, problems, and potential to unify physics once and for all. Among them, string theory is the most famous. It suggests that all particles are not points, but tiny vibrating strings whose different modes of vibration produce the variety of particles we see. String theory has the elegance of including gravity in a quantum framework. It naturally predicts a gravitonth, hypothetical quantum of the gravitational field, and it suggests extra spatial dimensions beyond the familiar three. But string theory's strength is also its weakness. It is mathematically rich but experimentally barren. The theory allows for an enormous landscape of possible universes, more than 500, each with different physical laws. Without a way to test which version corresponds to our own, it risks becoming unscientific, beautiful but untethered from observation. Still, its implications are profound. It supports the idea of a multiverse, where inflation gives birth to countless bubble universes, each a different solution of string theory's equations, and where our universe is simply one of many. In contrast, loop quantum gravity takes a more conservative route. Rather than introduce new dimensions or entities, it tries to directly quantize spacetime itself. It posits that space is made up of discrete loops, or quanta, of geometry-tiny, indivisible chunks woven together in a spin network. In this view, space is not continuous but granular, like pixels on a screen. This model offers hope for resolving singularities like those found in black holes or the Big Bang. It also preserves many principles of general relativity. But loop quantum gravity struggles to incorporate the other forces of natural electromagnetism, the strong and weak nuclear forces, into its framework. It is a powerful attempt to tame gravity at quantum scales, but it is not yet a full theory of everything. Then there is the holographic principle, a more radical idea rooted in black hole physics. It asserts that all the information within a volume of space can be described by data on the surface that encloses it. Applied to the universe as a whole, it implies that our three-dimensional reality might be a projection from a two-dimensional boundaria cosmic hologram. This idea gained traction through AD-S CFT correspondence, which shows a precise mathematical relationship between a gravity theory in a curved spacetime, anti-de Sitter space, and a quantum field theory without gravity on its boundary. While our universe isn't ADS, This framework has provided deep insights into how space-time and gravity could emerge from quantum entanglement and information. It blurs the distinction between what is and what encodes it, suggesting that reality may be less like a physical thing and more like a computational process. The idea is both awe-inspiring and deeply disorienting. Meanwhile, causal set theory and emergent gravity offer other avenues. Causal set theory proposes that space-time is fundamentally a discrete set of events connected by cause and effect, not a continuous fabric. Emergent gravity, proposed by Eric Verlinde, suggests that gravity is not a fundamental force, but an emergent phenomenon arising from changes in quantum information and entropy. These theories challenge deep assumptions, including the notion that space-time is fundamental. They imply that space-time, gravity, and even mass might not be real in the traditional sense, but the result of deeper informational processes. Amid all this, the debate about the universe's boundary rages on. Will we ever find a true edge limit to space, to time, to knowledge? If inflation is correct and continues eternally in some regions, then space could be infinite and the edge will always recede. If the universe is closed and curved like a higher dimensional sphere, then it could be finite but unbounded like the surface of a globe, with no edge, yet limited in extent. But even in that case, there's a deeper question. Is there an outside to the universe? A metaspace in which our cosmos sits? Or is the universe all there is, with no exterior at all? Some argue the boundary is not physical but epistemic, a limit to what we can ever know. We can only observe the part of the universe from which light has had time to reach us. This observable universe is a bubble about 93 billion light-years across, surrounded by unobservable regions that lie forever beyond our reach. No telescope, no experiment can penetrate that veil, not because we lack the technology, but because the laws of physics themselves impose that limit. This leads some scientists to speak of a cosmic horizon, not as an edge, but as a permanent fog. We can guess what lies beyond, but we may never confirm it. And so the boundary becomes philosophical, a frontier of thought rather than place. Yet scientists are undeterred. If anything, the confrontation has ignited a renaissance of creativity. New missions are already under construction. The James Webb Space Telescope, now operational, is revealing galaxies and structures from just a few 100 million years after the Big Bang, raising new questions about the formation of massive galaxies far earlier than expected. The Vera Rubin Observatory will capture vast swaths of the sky in motion, discovering supernovae, tracking dark energy, and mapping dark matter distributions. The LISA mission, a space-based gravitational wave detector, will listen to the universe in a frequency range where supermassive black holes collide and merge windows into the most extreme realms of gravity. These instruments will help test the limits of current theories. They may detect the signature of primordial gravitational waves ripples from the first instance of time, which would confirm inflation and constrain competing models. They might detect subtle deviations in the way gravity behaves at galactic or cosmological scales, pointing toward new physics. Or they may find nothing, forcing theorists to revise or abandon their models and to start again. That is the nature of the confrontation. It is not a war to be won, but a process to be endured, to be refined, to be lived. Meanwhile, physicists are building bridges between disciplines. Quantum gravity research now overlaps with quantum information science. Concepts like entanglement, entropy, tensor networks, and error-correcting codes are not just abstract math. They are tools for building spacetime itself. The idea that geometry emerges from entanglement is gaining ground. It suggests that space is not a container for things, but a web of relationships between things. Time, too, may be emergent from thermodynamic flow, from the evolution of quantum systems, or from the expansion of correlations across a quantum network. These ideas are speculative, but they are increasingly grounded in rigorous models, mathematical consistency, and connection to real data. Still, uncertainty reigns. We may be close to answers, sir. We may be further than ever. Some scientists warn that we are entering an era of post-empirical science, where theories are judged not by experiments but by internal coherence. Others insist that testability is essential, and that physics without prediction is not science. This debate will shape the future of cosmology, perhaps as much as the theories themselves. In the end, the final confrontation may not yield a single winner. There may be no one theory that explains it all. Or, the answer may be so alien to our current thinking that we will need to invent a new language to describe it. But that doesn't diminish the value of the search. In fact, it elevates it. Because this confrontation is not about solving a puzzle. It is about discovering who we are in a universe that is not obligated to explain itself. It is about building bridges between the known and the unknowable. It is about reaching toward a boundary that may never be touched, but must always be pursued. The future of cosmology will be shaped by this pursuit. It will be driven by questions that defy simplicity. What is time? What is space? What is matter? What is real? And it will be powered by collaboration between instruments and minds, between equations and experiments, between logic and wonder. Perhaps we will discover that the universe has no boundary at all, only deeper levels of structure. Perhaps we will discover that the laws of physics are not universal, but local, written in the dialect of each pocket universe in an infinite multiverse. Or perhaps we will discover that the edge we seek is not out there, but in the assumptions we carry with us. Whatever the outcome, one truth remains. The final confrontation is not a conclusion. It is a beginning. It is the point at which our models fail and our creativity begins. It is the moment when physics becomes philosophy, when questions become sacred, and when the universe stops being an object to be dissected and becomes a mystery to be honored. We may never find the final theory. We may never touch the edge, but in striving for it, we become more than we were, and that more than any equation or observation is the true future of cosmology. There is something timeless in the act of looking up. Before cities drowned the stars in their light, before telescopes turned the sky into data, before equations whispered secrets about gravity and time, human beings stood in the dark and asked the oldest question of all: what is out there? That question has never left us. It shaped myths, birthed gods, sparked revolutions in thought and fire. It pushed ships over horizons, built observatories on mountaintops, and accelerated particles to near the speed of light. We ask not because we are certain of the answers, but because we are certain we must ask. In that single-act curiosity, aimed toward the infinite, lies one of the deepest moral impulses of our species. To explore the cosmos is not just to understand stars or black holes or the beginning of time. It is to confront the unknown with humility and wonder. It is to search not just for facts, but for meaning. And it is to discover again and again that in the face of the infinite, we are small but never insignificant. Curiosity is not a luxury. It is not a trait confined to scientists or dreamers. It is the engine of human progress, the compass that has guided us from caves to cities to orbit. Without curiosity, there is no discovery, no art, no law, no civilization. It is what turns questions into insight and fear, into courage. And in science, curiosity is sacred. It is the first principle, the force that pulls us toward the edge of what we know and dares us to take one more step. That step might lead to new knowledge, but just as often, it leads to deeper mystery. Every answer unlocks a dozen new questions. The more we learn, the more we realize how much we don't know. This is not a failure. It is the mark of true inquiry. Mystery is not the enemy of knowledge. It is its partner. It is the space where wonder lives, where possibility breathes. A universe without mystery would be a universe without growth, without imagination, without the fire of discovery that makes life more than survival. And so, as we confront the grandest of all unknowns, the cosmos itself, we must carry that fire carefully. The universe is not obligated to reveal its secrets, and yet it does, slowly, generously, through the language of physics and the poetry of light. It speaks in gravitational waves, in redshifted galaxies, in the quiet hum of the cosmic microwave background. It hides its past in the spin of particles, the dance of atoms, the shadow of black holes. And we, brief creatures on a small world, dare to listen. That alone is a miracle. that we can build machines that detect the tremor of spacetime across 1 billion years, that we can simulate the first moments after the Big Bang, that we can speak the language of quantum mechanics and general relativity, even if we do not yet understand how they speak to each other. These achievements are not just technical, they are moral. They represent the highest aspirations of human thought. To reach beyond our limits, to seek truth for its own sake, to build knowledge not for conquest, but for comprehension. Yet there is danger in knowledge too. The history of science is filled with triumphs, but also with arrogance, with the belief that because we can understand, we are entitled to control. That nature is a puzzle to be solved, a machine to be mastered. Cosmic exploration teaches a different lesson. It teaches that the universe is not ours. It is not centered around us. It does not bend to our will. It is vast, old, and indifferent. And yet, in its very indifference, there is beauty. Because the universe makes no promise of meaning, and yet we find meaning in it anyway. We find it in the structure of galaxies, in the rhythm of planetary motion, in the harmony of physical laws that allow life to exist at all. And we find it in each other in the shared wonder of looking up and knowing that others are asking the same questions. The stars do not need us to shine, but we need each other to see them. And in that shared seeing, a kind of morality is born. What then are the lessons we learn from cosmic exploration, not just as scientists, but as humans? The first is humility. The universe is not built to suit us. It is larger, stranger, more complex than we ever imagined. Our lives are tiny flashes in cosmic time. Our planet is a speck in a galaxy that is itself a speck among trillions. This perspective can be frightening, but it can also be freeing. It strips away the illusions of grandeur. It reminds us that we are not the measure of all things, but a part of something immeasurably larger. And in that humility, we may find a deeper reverence for life, for the fragility of ecosystems, the miracle of consciousness, the responsibility we bear to protect our world and each other. The second lesson is unity. The universe does not divide itself into nations or religions or ideologies. Its laws apply equally to all matter, to all life. The light from distant galaxies does not care who measures it. The math of gravity does not change with politics. Science, at its best, transcends boundaries. It invites cooperation across continents, cultures, generations. It reminds us that we are all children of the same stars, made from the same atoms, shaped by the same cosmic forces. In an age of division and distrust, this reminder is not trivial, it is essential. It tells us that whatever differences we may have, we share the same sky. And perhaps, one day, we will share the same journey to the stars. The third lesson is courage. To ask the biggest questions is to risk never finding the answers. It is to walk into darkness, knowing the light may not come. But we go anyway. Because the search itself is worth it. Because wonder is worth it. Because to be human is to strive, to reach, to imagine something more. That courage does not only apply to space, it applies to every field of human endeavor, to justice, to art, to compassion, to truth. The same curiosity that drives us to explore other planets can drive us to explore new ways of living, new ways of healing, new ways of understanding ourselves and one another. The final lesson is responsibility. Cosmic knowledge is powerful. It changes how we see the world and how we act within it. It shows us the rarity of life, the thinness of our atmosphere, the interconnectedness of all systems. It tells us that Earth is not just a home, it is a miracle. A sanctuary in a universe of fire and ice, where molecules danced into minds and stardust became self-aware. To know this is to feel a duty not just to protect our planet, but to grow in wisdom. To ensure that our technology serves our values, that our exploration is guided by ethics, by empathy, by a reverence for the mystery we inhabit. Because the goal of science is not domination, it is understanding. And the goal of understanding is not power, it is harmony. And so, at the end of this long journey through the stars, through theories, discoveries, and unanswered questions, we return to something very old. The moral truth that exploration is not about escaping the Earth, but about understanding it more deeply. That the stars are not just destinations, but mirrors. They show us what we are and what we are not. They remind us that the universe is not a story with us at the center, but a vast unfolding into which we are lucky to play a part. And they call us, again and again, to the edge of what we know, not to conquer it, but to honor it, to listen, to learn, to wonder. This is the deepest meaning of exploring the unknown. It is not the final theory or the perfect model. It is not the edge of the universe or the key to quantum gravity. It is the act of reaching, the refusal to stop asking, the understanding that mystery is not something to be eradicated, but something to be embraced. Because in the presence of mystery, we grow. In the search for knowledge, we find humility. In the pursuit of truth, we find each other. And in the vast silence of space, we discover the voice of something eternal, the echo of curiosity, the heartbeat of wonder, the light of meaning, burning quietly in the dark. And maybe that is the greatest lesson of all, that the universe does not owe us understanding, but we owe it our attention, our reverence, our courage, because in exploring it, we explore ourselves. And that, more than any destination, is the journey that defines what it means to be human. The universe doesn't end with an answer. It ends with a question. Or more accurately, never ends at all. It just keeps opening, unfolding, revealing more complexity, more beauty, more depth, with every step we take toward understanding it. For centuries, humans have pursued the truth with an almost religious fervor, hoping to one day pull back the final curtain and glimpse the inner workings of reality in full. We have chased the theory of everything, the edge of the cosmos, the origin of time itself. And yet, the closer we get to what we once thought was the final chapter, the more we discover that the book of the universe doesn't end, it rewrites itself in real time. Every discovery is a door, not a destination. Every equation is a bridge to a deeper abyss of wonder. So the question arises, should we even want to close the book? Should we be content with never knowing it all? Or is the open-endedness of the mystery not a flaw, but the very heart of its value? There is a quiet power in unanswered questions, a kind of sacred energy in the space between certainty and doubt. When we leave a mystery open, we give it room to breathe, to evolve, to speak back to us in ways we couldn't have imagined. Some might see this as failure after all. Science is often judged by its ability to solve, to conclude, to define. But if we look at the greatest scientific minds in history, we find that they weren't satisfied with neat conclusions. Einstein, Newton, Hawking. They all ended their lives surrounded not by solutions, but by questions too large, too strange, too profound to be tied down. And in this, there is a lesson that perhaps the goal of cosmology, of science itself, is not to end the story of the universe, but to expand it, open it wider than any single theory, any final answer could ever contain. Because what have we really learned in our journey through the cosmos? We have learned that we are small but capable of thinking on scales larger than galaxies. We've learned that time had a beginning, but that questions about before may not even make sense. We've learned that 95% of the universe is composed of dark energy and dark matter entities we cannot see, touch, or explain. We've learned that space can expand faster than light, that particles can be entangled across billions of miles, that black holes can radiate information through quantum paradoxes we're only beginning to grasp. We've learned that the universe may be infinite, or it may loop in ways our minds can't yet fathom, that there may be other universes, or none. That we might be simulations, or quantum foam, or stories told by vibrating strings in 10-dimensional silence. And perhaps most humbling of all, we've learned that everything we know is only what we can know from one small bubble of space-time, surrounded by an immensity forever hidden behind the horizon of light and time. These aren't just facts. They are invitations. Invitations to think differently, to live with awe, to see our questions not as gaps in knowledge but as openings to meaning. Because in the end, mystery is not the opposite of truth, it is the source of it. Without mystery, there is no inquiry. Without the unknown, there is no progress. We are drawn forward not by what we've solved, but by what still resists solution. Mystery is the force that keeps the engine of curiosity running. It is the unlit path we walk not because we know where it leads, but because we must walk it. This doesn't mean we abandon the pursuit of knowledge. On the contrary, it means we pursue it more deeply, with more nuance, more reverence. It means we respect the complexity of the cosmos enough not to simplify it prematurely. It means we hold space for paradox, for ambiguity, for the possibility that the universe might be not only stranger than we imagine, but stranger than we can imagine. It means we accept that some questions may not have answers in our lifetimes, or ever, and we choose to ask them anyway. So what are the biggest takeaways from our journey through the infinite? First, that humility is essential. The cosmos dwarfs us in scale, age, and scope. Our greatest theories describe only fragments of its whole. Every time we think we've found the final word, the universe whispers another question. Our place in the cosmos is not central, but that makes it no less meaningful. Meaning does not come from size or position, it comes from attention, from our ability to notice, to wonder, to care. Second, that curiosity is our lifeblood. It is what transforms ignorance into inquiry, and inquiry into insight. It's what compels us to build telescopes, smash particles, decode spectra, write equations that stretch the limits of math and imagination. It's what allows us to look at a pinprick of light in the night sky and see a galaxy or a universe or a version of ourselves reflected across time. Third, that collaboration is the key. No one mind, no one nation, no one generation can solve the mysteries of existence. Cosmic exploration requires all of U.S. scientists, engineers, philosophers, storytellers, dreamers. It requires telescopes and particle accelerators, but also poems and art and conversation. It requires voices from every culture, every language, every worldview, because the universe belongs to all of us, and so does the quest to understand it. Fourth, that time is a gift. In a universe that may exist for trillions of years, we are given just a handful of decades. And yet, in that time, we can look back 13.8 billion years to the birth of space. We can send our minds to the end of time, to the edge of knowledge, and still return in time for breakfast. That is the miracle of consciousness, that we can wonder, that we can ask, that we can connect the dots between atoms and galaxies, between the micro and the macro, between the self and the infinite. Fifth, that uncertainty is not the enemy. It is the canvas. It is the space in which meaning is made. It is the background against which insight takes shape. The cosmos is full of uncertainty, not just in quantum mechanics, but in structure, in origin, in destiny. And rather than run from it, we learn to live inside it, to treat the unknown not as a threat, but as a partner in the dance of understanding. And finally, that space is not just a thing to be studied, it is a metaphor, a mirror, a metaphorical stage for what it means to be human. When we explore the universe, we are exploring ourselves, our capacity to love, to fear, to imagine, to persist. The stars are not symbols of distance. They are symbols of connection links in the chain of becoming that ties us to the beginning of all things. We are not separate from the cosmos. We are the cosmos, made conscious. The universe looking back at itself and asking, "What am I?" So, should the mystery remain open-ended? Yes, not because it must, but because it should. Because closure is not the point of exploration. Continuation is, growth is, transformation is. We do not explore the universe to shut it down. We explore to open ourselves up, to stretch our minds, our ethics, our sense of what is possible. Finality may belong to textbooks, but not to truth. Truth is alive. Truth evolves. And the truest truths of all may be the ones we cannot yet express, the ones we carry silently, in awe, into the dark. The infinite possibilities of space do not threaten us. They invite us. They remind us that there is more to learn, more to do, more to become. They give us permission to imagine not just other worlds, but better versions of this one. Versions where science is not weaponized but honored, where knowledge is not hoarded but shared, where exploration is not escape but return to the deepest questions of meaning, purpose, and belonging. In that sense, the universe is not just out there, it is in our questions, in our relationships, in our courage to live lives of inquiry and kindness. It is in the way we treat each other, in the way we educate the next generation, in the way we protect this fragile planet, knowing it is our only home. The stars do not need us to shine, but we need each other to make sense of the shining. And in that need, we find community, we find purpose, we find the deepest kind of truth, not the truth that ends a conversation, but the one that begins it. So let the mystery remain. Let it evolve. Let it grow, as we grow, into something even greater than knowledge, into wisdom. And when we look up, may we do so not in fear, but in reverence. Not in conquest, but in gratitude. For the silence, the vastness, the beauty. For the questions that lead us forward. For the universe, forever unfolding, forever unknown, and forever ours to wonder.